Alright, good afternoon everyone. So we will continue our tutorial for LO1 T2. But before I begin, let me share the screen first. Okay, so hopefully you can see the screen. All right, so last week we have already covered question number 1, question number 2. But number 2 we have covered. Number 3 as well. We stop at question number 4 halfway sebab kita hanya cover untuk single reactors only. So this week we will start tutorial. We will start tackling problem where we are now calculating or we are designing reactors in series. So similarly dengan konsep single reactor, reactor in series pun kalau you're given information which is conversion and minus RA, we can also determine the volume or any other information, any other parameter that is desired by the question using the information either dalam bentuk table atau dalam bentuk level sphere plot. Okay, so for question number 4, we have already tackled A and B, so let us go to C. Okay, so question C says, calculate the volume of the reactors if two CSTR are connected in series with an intermediate conversion of 40% and a final conversion of 60%. Okay, so now you know when we are talking about designing reactor, you have to be very careful. Either we are talking about designing single reactor ke, we are designing reactor, more than one reactor in series. Okay, so dalam soalan C ni sekarang dia dah bersiri. And in this series, we have two CSTR connected in series where the first reactor, okay, the conversion is 40%. So remember I told you, conversion daripada reactor pertama sampai the reactor just before the last reactor, we call it intermediate conversion. And the very last reactor tu, we will call it as final conversion. Okay, so dalam case ni ada dua reactor. So the first one, intermediate conversion. The second one will be final conversion lah. But let's say you have 3 reactor ke, 4 reactors ke. So 1 to the third one will be intermediate conversion. So X1, X2, X3. And the very last reactor baru kita panggil final conversion. So dalam case ni, X1 is 0.4, meaning reactor pertama will convert from 0 conversion of A to 40% conversion of A. Then remember I told you conversion tak reset. So that baki tu akan masuk reactor kedua. So the conversion tu akan increase daripada 40% A tadi, sekarang I convert to 60%. Okay. So they ask us to calculate the volume. So when we have 2 reactor, we have to calculate separately sebab kita kena tahu volume reactor pertama, volume reactor kedua. Okay, so the formula, this formula ni you kena tahulah, but of course in the test or exam, you can always refer to notes. So the formula is given for the first reactor, volume dia equals to volume CSTR1. We will write 1 and 2 supaya kita boleh differentiate so that you know you're calculating for the first one ke, you're calculating for the second one. So volume CSTR1 equals to FA0 X1 per minus RA X1. So it's very important untuk kamu indicate X1 ke X2 sebab ni reactor pertama dia mesti conversion X1. And then minus RA dia pun pada X1 supaya kamu jangan confuse. First reactor we just see X1 minus RA1. Okay, so since kita dah tahu FA0 tu kita dah solve last week. So FA0 we calculated from last week is equal to 35 mole per second because they give us CA0, they give us V0. Dia beri kita initial concentration of A, initial volumetric flow rate, we can calculate FA0. Okay, so perhaps you might ask, FA0 tu tak berubah ke? As long as dia tak beritahu any changes of CA0, any changes of V0, you may assume that the FA0 stay the same. Okay, kecuali dia kata okay, perubahan dalam CA0 or the changes in V0. So perhaps you have to recalculate. But if they don't say, then it's safe to assume that FA0 is the same. So kita gunalah FA0 yang sebelum ni, 35 mole per second. So X1 0.4 and then when my X is 0.4, apabila X saya 0.4, my minus RA is 0.04. Okay, so waktu kita ganti 0.04, you will get the volume of the first reactor 350 dm3. So kalau kamu perasan, if I try to relate back dengan chapter 3, dalam chapter 2 tu kita dah belajar sebenarnya, okay, conversion ni minus RE ni berapa. So misalnya chapter 2, that value of the minus RE is given for you. Okay, sebab tu chapter 3 sekarang, you will have to learn macam mana kita sebenarnya dapat nilai minus RE tu. So it's like become a bit hard. Chapter 2 terus guna nilai minus RE. Chapter 3 dah kena belajar macam mana sebenarnya nilai RE tu kita dapat. Okay, so now come back to the question. We go to the second reactor. So sekarang kamu dah kena ingat, part ni yang kamu jangan confuse. Bila dia dah in series, the second reactor or subsequently reactor ketiga ke reactor keempat ke, volume design equation dia dah tak sama. So part ni yang kamu kena ingat. Kalau kita kira untuk reactor kedua, third reactor, the formula has a little bit change, which I explained to you previously in the class. So what are the changes? Formula dia menjadi volume CSTR2 equals to FA0 and tambahan in the bracket X2 minus X1. Okay, so dalam reaktor kedua ni, dia punya conversion is from X1 yang tadi berubah kepada X2. Okay, tapi we write it as X2 tolak X1. Okay, katakan like I told you before, katakan kamu nak exam test, kamu confused X1 tolak X2 ke X2 tolak X1. Okay, sama je. Kalau let's say you write X1 tolak X2, kamu tahu nilai kamu akan dapat negatif sebab X2 akan sentiasa lebih besar daripada X1. Kan conversion meningkat, so means more reactor conversion will increase. So let's say you write X1 tolak X2, kamu akan dapat 0.4 tolak 0.6. Dia negatif. So kamu pun tahu kan volume reactor is impossible to be negative. Volume reactor mesti positif. So then perhaps it tell you, okay, saya akan terbalikkan. So jadi X2 minus X1. Okay. Then divided by, part ni pun jangan confuse. Minus RE tu mesti pada X2 sebab reaktor yang kedua. Okay, so that's why we write it as minus RE at my final conversion or at my X2. So FA0, kita still the same FA0. X2 0.6, X1 0.4 divided by minus RA when my X 0.6. So tengok je table, bila X 0.6 minus RA 0.025. So you replace with 0.025, you calculate, you will get the volume 280. So apa maksud dia? Maksud dia, if I have two CSTR in series, for the first reactor, katakan saya nak capai conversion 40%, my reactor must be at least 350 dm³. Okay. Then, let's say I nak sambung kepada second reactor where the conversion is 60%, the second reactor volume dia must be at least 280 dm³. So, done for part C. Okay, so dia not so difficult, I assume. Chapter 3 is much harder. Chapter 2 is quite straightforward, just that sometimes a little bit confused here and there sajalah. Right? So let us go to the next one, question D. Okay, so question D sekarang, calculate the volume of the reactor if two PFR are connected in series with an intermediate conversion of 60% and a final conversion of 80%. So tadi we do CSTR, now kita buat pula PFR but still in series and the conversion dah lain. So now in the D part, X1 60%, X2 80%, or in a simpler word, in the first PFR, dia akan convert from 0 to 0.6, 0 to 60%. Second reactor ni dia akan convert daripada baki yang tadi tu, yang 60% tu dia naikkan conversion kepada 80%. Okay, so how do we solve PFR reactors? Okay, so hopefully you still remember, volume PFR ni pun separate. Kamu kena kira reaktor pertama, kamu kena kira reaktor kedua. Okay, so volume of the first PFR equals to, kita still follow the design equation first. So equals to FA0 integrating pengamiran from 0 to 0.6 sebab reaktor pertama hanya convert daripada 0 kepada 0.6 dx per minus RE. Then don't forget sebab kan part integral ni kita nak solve, kamu ingat kan dalam level sphere plot dia adalah luas di bawah plot. So when it's the area under the curve, okay, area under the curve, we will use a Simpson one-third rule to measure it sebab it not so as straightforward. Kalau macam sebelum ni, kalau for CSTR is more straightforward sebab dia adalah linear equation. But for PFR dia dah integral and we can actually tweak the integral part into the Simpson 1/3 rule. So that's why we get it as FA0. Okay, FA0 tu depan tu masih kekal. Part yang integral tu sekarang kita tukar menjadi dalam bentuk Simpson 1/3 rule. So equals to delta x per 3 in bracket the 3 points. So I keep asyik repeat kan, sebab kenapa? Sebab I want you to really understand supaya that if kita tukar pun kamu masih boleh faham dia punya konsep. So the 3 points is first 1 per minus RA at your initial x. So in my this reactor, dia adalah convert daripada 0 to 0.6. That's why the first one become 1 per minus RA at 0, my initial x. And the last one, the third point, I always go to the third point, 1 per minus RA at my final x. So my final x is 0, not my final x, my x1 at the first reactor. Sebab kalau cakap final x, x2 pula kan, tak boleh. So it's my x1. So x1 saya 0.6. Sebab reactor saya, first one, convert 0, 0.6. And then the middle point you must remember ada 4. The 4 is always there. The Simpson 1/3 rule is 1, 4, 1. So 4 per minus RA at my middle x. So middle x tu yang kita kena cari. So you have initial 0, final x 0.6. Naturally the middle x is 0.3. So that's why it become 4 per minus RA when my x 0.3. And then the next one, delta x pula. So delta x pun saya repeat tapi I hope you understand. Delta x is the difference or the gap between initial x to middle x or middle x to the final x. So in our case, our initial x is a 0, middle x is 0.3. So the difference will be 0.3. Ataupun kalau kita tengok belakang pun sama. 0.3 to 0.6, the difference is still 0.3. So delta x 0.3. Okay, now that we have everything, then you substitute into the equation. FA0 35, delta x 0.3, jangan lupa delta x per 3, per over 3 as well. So 0.3 per 3. And then the points minus RA apabila 0, when it's 0.3, when it's 0.6, you just check the table. But be very careful, table tu nilai dia minus RA kan. So kita kena bahagi dengan nilai minus RA itu. Means 1 per minus RA when my x is 0. 1 per minus RA when my x is 0.3 and 0.6. So when you calculate, you will get the answer 517.15, meaning to say for you to have a PFR in series, the first PFR has to be at least 517.15 dm cube in order for you to have the intermediate conversion of 60% in the very first reactor. And then similar concept, katakan kamu tak sure penyerahan tu betul tak betul, I always encourage you, not only for my course, any other engineering courses or even engineering courses, try buat pembatalan unit. Mungkin setiap pathway, bukan setiap jalan kerja tu tak payah buat unit, tapi maybe the last one or the first one kamu letak unit, supaya biasanya first line tu kamu buat unit, sebab nanti kamu boleh tengok kamu buat pembatalan unit, if you calculate your unit tu betul, most likely jawapan tu betul. So in this case, when we cancel, you get the unit dimension dia volume, you memang nak calculate volume, so most likely your answer is correct. Okay. Then PFR2. Okay, PFR2 pun sama macam tadi CSTR, a bit tricky sebab dia dah tak straightforward. Sebab kena ingat konsep second CSTR ni dia dah convert daripada X1 tadi kepada X2. So that's why kalau kita tengok design equation dia, volume PFR2 equals to FA0. Dia integration dia from 0.6 to 0.8. Tengok dia dah tak start daripada kosong sebab reaktor kedua ni conversion tak reset. Dia hanya ambil baki tadi yang tidak balas tu, conversion tu dinaikkan lagi. So the bottom now is 0.6, the top is 0.8. Means daripada X1 kepada X2. dx per minus RA. Okay, so similar concept. The integral part will be changed into Simpson 1/3 rule. Tapi 1/3 rule ni kamu kena betul-betul faham macam mana kita nak letak nilai dia. So what do I mean by that? Okay, so on depan FA0 delta x per 3, I will explain a little bit later about the delta x. Kita pergi yang belakang dulu. Okay. So at the back, again sebab 1/3 rule, right? Kita ada 3 points. Okay, so the first one will be 1 per minus RA at my initial X at the second reactor. So second reactor dia kan, bottom limit dia kan X1. So dia menjadi 1 per minus RA at my X1, which is 0.6. Then I go to the last point, the third point, 1 per minus RA at X2. Sebab upper limit dia X2. So bottom limit X1, upper limit is X2 because the second reactor is converting from X1 to X2. So 0.6 the first, the last one 0.8. Middle ni pun sama, you have to find by yourself. So again, if I have initial 0.6, final 0.8, my middle X will be 0.7. So that's why dia jadi 4 per minus RA when my X 0.7. Okay, so part tu yang titik tengah tu, yang the middle X tu yang you have to really understand bagaimana kita boleh dapat the middle X. Sebab formula takkan tunjuk. So you really to know how we get the middle X. Okay, that part is done. Delta X. So delta X pun you have to be very careful. Sebab as I told you, delta X ni bukan middle point. Delta X is the difference between initial to middle or middle to final X. So my initial X is 0.6, my middle X is 0.7. The difference will be 0.1. Okay, sama juga. Kalau kamu nak tengok kat belakang pun boleh. 0.7, 0.8, the difference is also 0.1. So that's why delta X is 0.1. So again, ganti je nilai-nilai dia. On the minus RA, please check the table. Make sure you use the correct value. Alright, so when you calculate, you should able to get the volume about 395.67. Okay, so or in other words, if I want to increase my conversion from 60 to 80%, I need my second reactor to be at least 395.67 dm³. Okay, so we are done for question 2, part C, part D. Okay, so I give you about 1-2 minutes, okay, for you to just digest, or if let's say you're calculating, you can actually see it as you do the calculation. Okay, I will come back in about 1 to 2 minutes.
Doktor.
Yes, yes.
Tak dengar.
Dengar. Tak ada, tadi saya bagi break 1-2 minit sebelum mula balik. Nanti saya tahu balik. I give you break to see the questions. Terus saya diam. Okay. Alright, so back from the break, actually I give you 1 to 2 minutes break to actually see the question, but okay lah, 2 minute break pun dah start. So I will go to the next question. Alright. Okay, right. So we go to question number 5. Okay, so question number 5, you see now kita dah different sikit, right? Because now we are using plot. So kamu ingat je, kadang-kadang dalam information tu dia dalam bentuk table or in the form of plot. Tapi yang plot tu apa beza dia? Kalau table X minus RA, kalau plot dia akan 1 per minus RA. Part tu je kamu kena ingat. Dia mesti 1 per minus RA versus X. Okay, so bila nak ambil information tu, nak ambil maklumat daripada plot tu, kena ingat. Okay, so let us go to the question. The gas phase reaction is given as follows. A produce B. Okay, so dia kata the irreversible reaction is carried out isothermally in a flow reactor at an initial rate of 10 dm³ per second. So let me explain the information. Okay, first irreversible reaction. So at the moment you just learn irreversible. Kita belum belajar reversible. But just to explain, irreversible reaction means the reaction goes a forward direction. Okay, so all of my reactant will be converted into product. There won't be any reverse reaction. Backward reaction tu tak ada kalau irreversible. Okay. Next, dia kata isothermally. So isothermally, you know, iso means same. Thermal tu macam heat lah kan? Heat. So it means same heat, or we can say that there's no heat release or supplied to the reactor. Hence, the temperature is constant throughout the reaction. Okay, so that's the second information. Means temperature yang masuk, temperature yang keluar semasa tidak balas adalah sama. Okay. Next, dia kata initial rate 10 dm³ per second. So, I already start training you. From unit, tengok kenal dimension, teka nilai dia. Kan teka, tahu nilai dia. So, dm³ per second, dm³ is volume, second is time. Volume per time, volumetric flow rate. Tapi volumetric flow rate pun you have to be careful sebab volumetric flow rate can be initial, can be final because volumetric flow rate can change according to the phase. So in this case, kamu kena ingat dia kata initial, right? So this is initial volumetric flow rate. V0 yang kecil tu sama dengan 10 dm³ per second. Okay. Next part, the feed mixture consists of 45 mole % inert and the balanced reactant A at 40 Celsius. So interestingly, dia kata feed kita tu terdiri consists of 45 mole % inert, okay, and the balance A. So maksudnya apa? Although my reaction is only with reactant A yang bertindak balas, tapi we don't use pure A. Instead, in that mixture tu also have other compound that is not involved in the reaction, tapi dia ada dalam sistem tu. So we call it as inert, and dia kata inert tu 45 mole %. So means inert normally kita guna I kan. So Yi0 tu 0.45. Hence Y0, so Y0 akan jadi 1 minus 0.45 or 0.55. Maksudnya asal tindak balas tu, sebelum tindak balas berlaku, we have 45 mole % inert and 55 mole % A. Okay, so that's the meaning of the center. Dia beritahu kita sebenarnya dalam tindak balas tu asalnya tak ada, bukannya semua A, ada juga campuran inert. And the Yi0 0.45, Ya0 0.55. Okay, done. And dia kata temperature 40 Celsius. So similarly, temperature pun boleh berubah semasa tindak balas. But in this case, dia kata isothermal, right? So initial temperature, final temperature pun 40 Celsius. Okay, next one. The initial partial pressure of the inert is 5 atm. Okay, dia beri kita pressure, tapi dia beri kita initial partial pressure of inert. So maknanya tekanan inert yang awal-awal tu, kita punya inert tu pada asalnya tekanan dia adalah 5 atm. Okay, itu tekanan daripada inert kita. Okay, so example dia mungkin kalau kamu confused, example dia senang je. Kalau tindak balas tu let's say melibatkan oxygen gas, tapi kita tak guna pure oxygen, kita guna air. So bila kita guna air, you know that kita ada oxygen, kita ada nitrogen, right? So tindak balas tu oxygen, tapi di sebalik oxygen tu ada juga nitrogen that we have to consider. So let's say dalam kes ni, pressure nitrogen tu adalah 5 atm and nitrogen tu punya mole percent 45 mole %. Okay, something like that. Okay, alright. So next, they give us the Levenspiel plot. Alright, so Levenspiel plot ni sama lah kan? For every conversion, kita tahu berapa 1 per minus RA dia. Contohnya, katakan pada 0.1 conversion, 1 per minus RA is 2.7, so on and so forth. Okay, so the question says, the reaction was conducted in 2 CSTR in series. Determine the volume of both reactors required to achieve 60% conversion at the first reactor and 80% overall conversion at the second reactor. So now kita ada 2 reactor in series And by now you should know, right? Means reaktor pertama tu X1 0.6. Means reaktor pertama convert daripada kosong kepada 0.6. And second reactor is converting from 0.6 to 0.8. And they want us to find the volume. Okay, so now I always tell you, katakan kamu tak tahu macam mana nak mula soalan. Okay, katakan kamu tak tahu nak mula. It's also important for you to perhaps know apa equation yang berkait. Okay, so kamu tahu kalau kita nak kira volume reactor, dia mesti will start with the design equation. So let's say we start first with the design equation. Let's say kamu tak pasti sebab maklumat banyak sangat. Okay, kita jadi confused kan, tak tahu mana satu nak guna. Kita tengok dulu equation apa yang kita boleh guna. So you know that kalau nak kira volume reactor, mestilah start dengan design equation dia. Okay, so kalau nak kira untuk volume reactor first CSTR volume, formula dia yang tadi kita dah buat kan, FA0 X1 per minus RA at X1. Okay. So again, I always tell you, kalau kita nak selesaikan engineering questions, alright, and we only have one equation, kalau kita nak selesaikan, kita kena make sure the other all unknown mesti ada nilai. Hanya satu unknown yang kita nak cari saja yang akan ditinggalkan as unknown. So in this example, kita nak cari volume reactor tu sebab kita nak tahu volume reactor 1, volume reactor 2. So volume CSTR1 tu dah jadi unknown yang kita nak cari. So left hand side is what we want. So by right, the right hand side, all the unknowns tu kita kena ada nilai. Kalau kita tak ada nilai, kamu tahu we cannot solve this problem. So let us go one by one. Okay, so let's say kita tahu from the question, X1 kita dah tahu sebab dia katakan dalam first reactor kan conversion 60%. So X1 dah tahu 0.6. Okay, settle. Then bawah, naturally kalau dah tahu X, mesti dah tahu minus RA kan sebab kita tengok daripada plot. So from plot we know when my X 0.6, my 1 per minus RA 8.85. Okay, so the bottom one pun saya dah tahu. So tinggal FE0. Okay, so now FE0 yang jadi masalah. Okay, why? FE0 tu apa? FE0 tu inlet molar flow rate of A. Okay, so if you realize kalau inlet molar flow rate, dimension dia mesti mole per time. Okay, so kalau kamu perasan dalam soalan, kita tak ada satu pun information yang beri kita directly mole per time. Ada pun sini dm cube per second, dm cube volume per time. Tapi kita kalau nak guna FA0, dia mesti mole per time. Okay, then perhaps you remember FA0 kan kita boleh cari kalau kita tahu CA0 dan V0. Okay, kita dah belajar soalan tadi pun sama kan? Kalau tak ada FA0 tak apa, asalkan tahu CA0, tahu V0. Okay, initial concentration, initial volumetric flow rate. Okay, so now kamu dah tahu satu lagi perkaitan. Tak tahu FA0 tak apa. Ada satu lagi perkaitan sebab FA0 sama dengan CA0 V0. Okay, so now we study the second equation. Okay, second equation ni pula V0 dah tahu 10 dm cube per second. From question dah bagi 10 dm cube per second. Done. Okay, dah tahu. Then CA0 pula. Okay, CA0 initial concentration. Dalam soalan ni tak beri pula concentration, right? Sebab kalau dia nak bagi, dia mesti dalam bentuk mole per volume. Kalau tengok, tak ada pun satu information yang dalam bentuk mole per volume. Okay, so dah satu lagi pening. Tadi equation pertama dah tak dapat, jadi equation kedua. Equation kedua pun tak settle lagi sebab sekarang tak tahu CA0. Okay. On the other hand, although we don't know CA0, tapi kamu dah pernah belajar dalam chapter 2 yang beginning. Kalau kita ada gas phase, we have gas phase, we know temperature, we know pressure, we can find the concentration using ideal gas law. Okay, harap kamu masih ingat kita belajar chapter 2. Tak tahu, asalkan tahu temperature, tahu pressure and dia adalah gas. Dia mesti gas. Liquid pun tak boleh guna sebab equation ni daripada ideal gas law. The equation says kita boleh cari CA0 equals to YA0 P0 per RT0. Okay. So kalau kamu ingat ideal gas law ni kan ada dua version kan? Kenapa ada dua version? Sebab dia punya konsep perbezaan version tu sebab depends on pressure yang kita tahu. Okay, kamu kena faham betul konsep ni. Kalau kita nak cari concentration of A initially, yang pressure tu mesti pressure from A only. Okay, so if in that example, letakkan dalam soalan tu, you know your partial pressure of A, the initial partial pressure of A, kita terus guna directly. So jadi PA0 per RT0. On the other hand, let's say you don't know the pressure of A in the system initially, but you know the initial total pressure. Katakan kamu tahu initial total pressure tu berapa. Tapi kamu tak boleh guna directly terus initial total pressure. Sebab ingat saya kata mesti tahu pressure A. So what happen? That's why they multiply with YA0 P0. YA0 P0 tu bersamaan dengan PA0 sebenarnya. So if let's say you're given P0, initial total pressure, you must multiply with YA0, mole fraction of A. Baru kita dapat sebenarnya pressure yang datang daripada A. Okay. So settle part tu. Okay, now second part pula nak solve equation ni lah kan. Okay. To solve this, first of all, kalau kamu perasan, okay, YA0 kita tahulah kan sebab dalam soalan dah kata 45 mole percent inert balance A. So YA0 saya tahu sebagai 0.55. But then next, P0, initial total pressure. Kalau kamu perasan dalam soalan, kita tak diberi initial total pressure of, kita tak diberi partial pressure of A pun tak bagi, initial total pressure pun dia tak bagi. Apa yang dia bagi? Dia hanya bagi partial pressure inert. So mungkin kamu rasa confused kan? Dia bagi, kita nak tahu, kalau nak kira tu mesti kena tahu pressure A ataupun total pressure. Tapi dia tak bagi kita dua-dua ni. Dia bagi kita partial pressure inert. Tapi kita tak boleh guna partial pressure inert sebab kita nak kira keperkatan A mesti pressure A. So how do we solve this? Okay. So now you have to come back a little bit to understanding concept. Remember I told you, kalau YA0 darab dengan P0, kita dapat PA0 kan? YA0 darab total pressure, dapat partial pressure A. So same concept. Kalau saya buat YI0 darab dengan P0, saya dapat partial pressure inert. So YI0 mole fraction inert darab dengan total pressure, saya dapat partial pressure inert. Since saya tahu partial pressure inert, saya tahu YI0, by right I can dapat YA0. Akan dapat P0, sorry. So YI0 darab P0 sama dengan PI0. Tahu PI0, tahu YI0, I can get P0, the initial total pressure. So that's why I will use the correlation to get actually my the initial total pressure of the system as 11.1 atm. Or in other words, daripada jumlah tekanan ataupun dalam erti kata yang lebih senang, dia actually berkadaran. Maksud saya, kalau mole fraction dia 45%, 45 mole percent ni bersamaan dengan 5 atm untuk inert. Okay, so 45%, 5 atm. Okay, so kalau saya nak tahu total pressure, 100% kan, darab silang je. So 100% apa sebenarnya yang kamu nak cari? Kalau kita nak cari jumlah tekanan, kamu akan buatlah. Kita akan buat 45% bersamaan 5 atm. Kalau 100% dapat total pressure. Pressure daripada A. Sama je, dapat je, sama je konsep dia. Tapi kalau kamu terus dapat pressure from A, kamu akan terus ganti sebagai PA0. Kalau kamu kira as 100%, itu adalah P0. Tapi bila kamu kira P0, nak masuk dalam equation ni, jangan lupa darab dengan YA0. Okay, so that's why I always tell you, engineering ni tricky in that sense. Tak semestinya apa yang saya ajar, kamu kena ikut bulat-bulat. You might actually use to find PA0. Sama je, dapat juga. Or for my case, I dapatkan P0. Sama je. So don't think there's only one way to solve question. There's so many ways for you to solve question, but the final answer shall be the same. Okay, so done on the pressure. I hope you understand the pressure part. That's actually the tricky part of this question lah. Okay, so divided by RT0. So as I always tell you, R ni pun sometimes you get confused because you might have a lot of R value when you Google up on it. Okay, so again macam saya, I will Again, there's no fixed rules on how to choose the R value. As long as kamu kena make sure unit tu consistent and kamu boleh cancel unit. Kalau tak unit tak consistent, kamu kena buat conversion. Okay. For my case, I will always choose my R value according to my pressure unit. Supaya saya punya tekanan punya unit akan cancel automatically. So for the case when it's ATM, the R value is 0.082 ATM dm cube per mole Kelvin. Okay, then next kan T naught. Okay, T naught ni pula unit dia saya akan ikut unit R saya. So maksudnya itu kata lain, pilih nilai R ikut unit pressure. Unit temperature tu ikut pula nilai R. So unit dalam R. So dalam R gas constant, unit temperature dia Kelvin. So temperature tu saya convert terus kepada Kelvin daripada Celsius because the temperature is given in Celsius as 40 Celsius. So I convert into Kelvin by adding 273.15. And don't forget, I always tell you, nilai R and conversion factor, kamu tak boleh, you cannot take, you must take the exact significant figure. So kalau 8.314, please take 8.314. Dan bila kamu convert kepada Kelvin, must plus 273.15. Kamu tak boleh just letak plus 273. A lot of previous semesters, ramai student buat macam tu, dia tambah 273. Tak boleh, dia tambah 273.15. Okay, so when you do, you will get CA naught as 0.238. But don't forget, you don't pula stop sampai kat sana pula. Kita punya mission nak cari FA naught, belum settle. Dah dapat CA naught, come back cari FE naught. Okay, so FE naught akan menjadi CA naught multiply with V naught, right? So CA naught 0.38, V naught 10, you will get FE naught 2.38 mole per second. So again, both calculation, make sure you check the unit to be consistent. Do cancellation, make sure it's consistent. Once you get FA naught, then baru masuk balik design equation. So you can see actually this question sort like reverse engineering. Pergi design equation, tak solve ni cari equation lain. Tak solve lagi cari satu equation. So you sort like doing reverse engineering punya problem scale, right? So then we solve, right? So FA naught 2.38 settle, X1 0.6 settle, and then this part don't forget sebab when you check from the plot, when my X 0.6, 1 per minus RA2 12.64, sorry, 1 per minus RA2 adalah 8.85. So you multiply directly with 8.85. And then you will get the volume as 12.64. Okay, so settle. So soalan ni dia susah part atas. Tapi kamu bayangkan katakan kamu dapat salah CA naught. Or kamu dapat salah FA naught. Basically yang bawah tu semua dah salah lah. So be very careful with answering reaction question. Kamu tak boleh salah at any step. Especially kalau part yang awal-awal. So bayangkan kalau part ni kamu salah CA naught ke, kamu kira salah FA naught, part bawah mesti confirm dah salah sebab menggunakan nilai tu kan. Okay, so be very careful about that. Right, so next one, volume CSTR2. So formula sama kan, volume CSTR2 equals to FA naught, but in bracket sekarang X2 minus X1. So reaktor kedua, convert from X1 to X2. Okay, divided by minus RA at my X2. So FA naught, volume CSTR2 sama dengan FA naught tak berubah. So again, saya kata kalau dalam kes ni CA naught tak berubah, V naught tak berubah, FA naught is always the same. So FA naught, then multiply with X2 minus X1, 0.8 minus 0.6, multiply with 1 per minus RA when my X at 0.8. Okay, so tengok plot balik. Bila X is 0.8, 1 per minus RA dia adalah 20. So ganti saja dengan 20, you will get the volume 9.52. Okay, so that's all for question number 5. Okay, not hard I suppose, but again, itulah mungkin part atas tu is a little bit confusing. Okay, so as the same as previously, 1 to 2 minute breaks for you to understand, and then I will go to the next question. Okay, saya tutup mic, saya tutup kamera kejap, nanti saya akan balik dalam masa 2 minit. Alright, so we go to the next question. Okay, so it's okay if you have if you take more time to solve it, it's very normal. So as I told you lah, at least daripada session ni kamu dengar je, kamu faham je. Kalau tak sempat kira pun tak apa. Yang more importantly is actually, if I tell you honestly, kamu kena faham, sebab nanti kalau soalan test exam memang takkan keluar directly, but understanding tu kalau kamu faham macam mana kita twist question pun, you will understand why this is important. Because you know, right, when you work in the real industry, problem comes in many types, in many set. So pemahaman tu yang penting, bukan penghafalan. That's why if you realize formula saya tak pernah suruh kamu hafal. Memang you don't need. Even if physical exam pun, I will never expect you to memorize any equation. Sebab in the real world, anything you can get at the tips of your hujung jari tu dah boleh dapat. Tapi why are you hired? Because your experience in handling the problem. So problem tu tak boleh Google. Problem tu yang kamu kena solve berdasarkan pemahaman soalan. Okay? So hopefully that's important that I want to impart. You understand the concept. Tapi lepas tu macam mana twist pun, you by right you can do the question. Okay, so let us go to the next question. The reaction is conducted in 2 PFR in series. So tadi single, sekarang series. Tadi CSTR, sekarang PFR. Okay, so dia kata determine the space-time for both reactors required to achieve 40% intermediate conversion, overall conversion 80%. Okay, so now dia dah lain sikit kan. Okay, apa maksud saya lain? Okay, reaktor bersiri tu masih sama. Intermediate conversion, overall conversion also still the same. Tapi yang beza dia, sebelum ni we calculate volume, but this one dia nak kita calculate space-time. Okay, so you probably, I have already taught you about space-time, tapi kita tak pernah guna space-time untuk design reactors kan. So now dia nak kita guna space-time, kita nak cari space-time. Okay, so this is where you come, you have to somewhat apply and connect these two information. Okay, what do I mean? Okay, kita start dulu dengan design equation for PFR first. So design equation PFR kata volume PFR1, again sebab ada dua reaktor, of course space-time dia akan berlainan kan. Space-time reaktor pertama, space-time reaktor kedua akan berlainan. Okay, kita cari untuk space-time reaktor pertama. So the volume of the first reactor equals to Fe0 integrating from 0 to 0.4 dx per minus Ra. Okay, so itu design equation kita yang kita guna untuk cari volume. Okay. Then next, kita ingat pula macam mana nak cari space-time. So I hope you still remember. Kalau tak remember pun tak apa. Space-time is actually tau, kita guna tau. Tau equals to volume reactor divided by inlet volumetric flow rate. Ingat dia volume, volumetric flow rate. So kita tahu kalau kita nak cari space-time untuk PFR pertama, dia akan menjadi volume PFR1 divided by inlet volumetric flow rate. Okay, so you can see here somewhat dah ada connection kan. Kita dah tahu volume. Okay, space-time ada volume. Tapi space-time pun ada inlet volumetric flow rate. Okay, kamu tengok equation design ni tak ada inlet volumetric flow rate kan. Dia ada Fa0 sahaja. Fa0 dengan integral. Okay, then it tells you kalau saya nak bentuk soal equation ni, or I want to twist the equation, I must introduce V0 first. I kena introduce inlet volumetric flow rate dalam design equation ni. Baru somewhat saya boleh twist and turn kemudian. Okay, then it has to tell you how do I introduce V0 to the equation. Then perhaps you remember Fa0 kan sama dengan Ca0 multiply with V0. So instead of writing in the form of Fa0, design equation tu, saya juga boleh tulis dalam bentuk Ca0 multiply with V0 sebab that is equal to Fa0, right? Ca0, V0, integral punya part tu masih kekal sebab kita hanya tukar part Fa0. Okay. So then you ask, kalau dah dalam bentuk ni, kalau kamu perasan, okay, kiri on your left, on my left, volume. On my right, Ca0, V0, integral. So can you imagine if the V0 on my right hand side, I transfer to the left. So sekarang kalau kat bahagian kanan dia atas kan, kalau saya pindah ke belah kiri ke bahagian volume tu, dia akan jadi apa? Dia akan jadi bahagi kan? Sebab mathematics, right? You go opposite way, you become division. So akan menjadi volume PFR1 divided by inlet volumetric flow rate. Kalau saya pindahkan volume kepada inlet volumetric flow rate, itu kan sama dengan space-time. So now on the left hand side, saya dapat space-time dengan hanya pindahkan V0 from right to left. So right, settle, dah dapat space-time apa yang kita nak. Left hand side. Right hand side tinggal apa? So right hand side akan tinggal Ca0. Kan Ca0 tak pindah. And then V0 dah pindah, integral tak pindah. So the integral and CA0 remains on my right hand side. So means kiri dah dapat space time. Yang bahagian kanan sekarang tinggal CA0 integral part. So dan lupa. Kita boleh solve dah kan? Tapi kita nak solve dah tak straightforward sebab CA0 tu dah remain lah kan. Integral part tu kita tukar jadi bentuk Simpson 1/3 rule. Sebab integral part tu yang akan bertukar menjadi Simpson 1/3 rule. Yang CA0 tu remains. So now you have already converted from volume reactor punya design equation menjadi equation untuk space time. Okay, dengan pindah V0 from right to left. Okay, so the space time for the first PFR equals to again CA0. So CA0 tadi kita dah kira daripada soalan part 1 tadi dah ada CA0. Kita boleh guna CA0 yang sama because they didn't say any changes. My CA0 I can use. And that akan menjadi delta X per 3 in bracket we are integrating for the first reactor 0 to 0.4. Okay, so akan menjadi first point 1 per minus RA at my initial X 0. Last point 1 per minus RA when my X is 0.4. And the middle X will be 0, 0.4, middle X 0.2. So 4 per minus RA at my middle X 0.2. So tengok kadang-kadang saya pun tersasul yang tengah-tengah tu 1. Actually dia mesti 4. 4 per minus RA at middle X. Okay, so done kan? Then delta X pula. So delta X ni saya selalu repeat sebab the thing yang saya selalu repeat tu bukannya apa. Sebab that thing is the one that students sometimes terlupa atau terconfuse. So delta X 0 to 0.2. Okay, middle dia 0.2 kan? 0 to 0.2, beza dia 0.2. 0.2 ke 0.4, the difference is also 0.2. So delta X jadi 0.2. Okay. So the rest you just look from the table, look from the plot, but don't forget plot tu adalah 1 per minus RA. So nilai tu kita dapat, kita terus ambil nilai tu directly, dah tak bahagi. Okay. And then don't forget yang tengah tu kena multiply with 4. Right. So then you get the space time, dah nama pun space time kan. So mestilah unit dalam bentuk masa. But let's say kamu terconfuse ke, kamu tak sure, buatlah unit pembatalan. So you can see I can cancel my mole, I can cancel my dm cube, I'm left with second. So the space time is actually 0.33 second. Meaning to say, if I have two reactor PFR in series, reaktor pertama tu holding time dia untuk capai conversion 40% reaktor pertama, I need to hold the reactant. Okay, imagine that reactant I hold in the reactor only for 0.33 second. Dah capai 40% conversion. Okay, so done. So reaktor kedua, okay, let us go reaktor kedua. So reaktor kedua sama space time juga kan. So we want to find space time for the second reactor. So why different? Sebab space time kan volume kepada inlet volumetric flow rate. Kamu tahu volume berubah, space time pun definitely akan berubah. Okay, so it become volume. Again kita start pada design equation balik lah. So volume PFR2 equals to FA0. Integrating sekarang reaktor kedua akan convert from 0.4 to 0.8. So kamu akan tulis 0.4, 0.8 dx per minus RE. So same concept. Kalau nak dapat space time, I cannot leave it as FA0 sebab tak ada V0 tak boleh buat jadi space time kan. So kita akan jadikan FA0 in the form of CA0 V0. Integral part kekal. Okay, so why I do that? So that now the V0 I can move from right to left. So when I move to the left hand side, dia akan menjadi volume per inlet volumetric flow rate. So volume per inlet volumetric flow rate adalah space time for my second PFR. Okay, so dah dapat. So right hand side pula jadi tinggal CA0 dan my integral part. So then equals to CA0 tu kita kekal. Integral part is the one that becomes Simpson 1/3 rule. So dia akan menjadi delta X per 3. So this part you have to be very careful. Initial dia X1 is 0.4 kan. So it become 1 per minus RA when my X 0.4. The last point 1 per minus RA when my X 0.8. So the middle will be 4 per minus RA at middle X. So kalau ada 0.4, final dia 0.8, the middle X will be 0.6. Okay, so that's why it becomes 4 per minus RA when my X 0.6. So by now, I hope you already know, right? Kita dah ada ni paling senang kita just make sure kamu cari, you use the plot to get the value. Okay, what about delta X? So delta X yang kita kena be very careful. So delta X dia 0.4 to the middle 0.6, beza dia 0.2. If you look at the back pun tak apa, 0.6 to 0.8, the difference is 0.2. So that's why your delta X is 0.2. Okay, so the rest sama je, say not masih sama. Just like make sure you look at the plot apabila my X 0.4, 1 per minus RA is 5.13, and then so on and so forth. Okay, so you replace the value, you will get the space-time of the second reactor as 0.96 second. Meaning, kalau katakan dalam reaktor kedua, kamu nak capai conversion yang tadi 40% kepada 80%, you have to hold the reactant at least 0.96 second in your second reactor, only you will achieve the desired conversion. Okay, so this question is something different, somewhat different from what you previously do, right? So sebelum ni, kamu just kira volume. Okay, tapi kamu ada baca pasal space time. So this question helps you to actually relate. Bukan helps you, it asks you the question in the form where kamu kena relate kedua-dua equation ni pada waktu yang at the same time. Okay, so done for part B, alright. Kamu jangan lupa kalau kamu nak soalan dalam VLE saya tu, saya embed video. Bila kamu klik kepada title tu, akan keluar soalan dia. Sama macam notes juga. Bila kamu klik on the title, let's say saya letak lecture chapter 2, lecture chapter 3, when you click on the title, akan keluar slide. When you click on the tutorial, will come out the tutorial question. So I worry you don't know where to get the question from. Okay. So next question is question number 6. Right, so question dia kata, okay, a mixture consists of pure A enters the reactor. Okay, so again, dia bagi kita pure A je asal. So senang sikit lah, kurang masalah dah pure A. Okay, dia kata, they give us the table of information, sama je, conversion minus RE. Okay, they say in the plant, there are available 250 dm³ CSTR reactor or 250 dm³ PFR reactor. Okay, so dia kata sekarang dalam plant ni pula dah ada reactor tu, and the reactor is, we have 2 CSTR, we have 2 PFR. All 4 reactors ni equal volume of 50 dm³. Okay, so kamu kena faham dalam real world application, not all the time your company will allow you to purchase new equipment. It's very rarely kamu boleh dapat purchase equipment baru. Most of the time, let's say if the company wants to produce new kind of product ke, dia nak innovate ke, you will always need to rely on the available resources. Sebab tu kamu, dalam contoh kes ni macam tu, kamu dah ada volume, kamu dah ada reactor tu, kamu nak tengok sama ada can we use or we cannot use. Okay, but let's go further for the question, you will understand better. Okay. To achieve higher conversion, overall conversion of A, the technologists decided to use either one of the reactor in series. So dia kata, let's say you imagine you are the technologist, you want to use either one of these configuration. Sama ada nak guna 2 CSTR ke atau nak guna 2 PFR in series. And empat ni reactor ni kita dah tahu volume dia. Okay, dia kata, it's targeted that the A intermediate conversion at 20% and overall conversion of 80%. So ada syarat dia. Syarat dia reaktor pertama ni sama ada reaktor pertama CSTR ke, reaktor pertama PFR ke, dia punya conversion mesti 20%. And the second reactor conversion dia 80%. So that is our boundaries. 20% first reactor means first reactor to X1, 20% means daripada 0 to 0.2, and the second reactor must be from 0.2 to 0.8 regardless of which configuration you use. And initial flow rates of 1.5 mole per second. So soalan ni dah senang sikit, dia terus bagi kita FA0. Kenapa? Mole per second kan mole per time. Mole per time is molar flow rate. So tak payahlah nak kena cari FA0. Question ni dah bagi kita FA0 1.5 mole per second. So dia kata, evaluate which reactor configuration can be used to achieve the targeted conversion by comparing the calculated and available reactor volume. State the reason. Okay, so dia kata sekarang, okay, you ada let's say you are the technologist, dia tanya kita sekarang mana reaktor kita boleh guna. Dengan boundaries dia mesti 20% first reactor, second reactor dia mesti 80%. So can we use either 2 CSTI in series ataupun 2 PFR series yang dalam plan kita. So how do we do that? Okay, so maksudnya you have the available reactor volume kan, 50, 50, 50, 50. So when you calculate your reactor volume, yang bila kamu kira reactor volume yang kamu calculate tu adalah minimum volume yang diperlukan for that reaction. So for example, meaning to say the volume that you calculate, okay, must be equal or smaller than the available reactor, or the other way around, reactor yang ada dalam plan tu must be at least equal or bigger than the calculated volume. Okay, or in other words, the available reactor volume must be equal or bigger than the calculated volume. Okay, so contohnya katakan volume reactor yang kita ada 50 kan. Let's say kamu kira volume yang kamu perlukan adalah 40. So you can use, sebab kita ada reaktor 50, kita kira kita hanya perlukan 40, we can use. But let's say you calculate reactor volume minimum yang diperlukan adalah 60 dm3. But in our plant, the reactor volume is 50 dm3. So tak boleh lah sebab volume minimum yang diperlukan lebih besar daripada volume yang ada dalam plant kita. Okay, so this is what we need to do. Kira volume, the volume that we calculate, you compare with the available volume. Kalau dia adalah sama atau lebih besar, you can use. If not, we cannot use. Okay, so means in this case, if a bit tedious. Kamu kena kira CSTR yang 2 tu, lepas tu kita kira PFR yang 2. Okay, so let us start first with CSTR lah kan. CSTR yang paling senang. Okay, so CSTR, kita kira volume CSTR pertama. Okay, volume CSTR pertama, FA0 X1 per minus RA at X1. Okay, so FA0 directly dah bagi 1.5. X1 0.2 dalam boundary stick kan dah kata X1 0.2. So when my X 0.2 minus RA saya adalah 0.050. Kena make sure bila kamu tengok table tu kamu kena ingat table tu nilai minus RA itu bergantung kepada X yang kita nak. Kalau kita nak X 0.2, kita tengok X 0.2 minus RA dia 0.050. Okay, so you will replace, you will get the volume 6 dm3. Maksudnya minimum volume reactor yang diperlukan if you want to achieve 20% conversion hanya 6 dm3. Reaktor kita punya size 50, definitely more than enough, right? So setakat ni kita boleh conclude reaktor pertama CSTR tu kita boleh gunakan. Okay, so kita check pula reaktor yang kedua. Kita kena make sure dua-dua reaktor tu fulfill the requirement, baru we can say we can use the configuration. Kalau satu fulfill, satu tak fulfill pun tak boleh sebab kita mesti guna dua bersiri. Okay. Next one pula, kita kira CSTR kedua. So CSTR kedua will be equals to FA0 X2 minus X1 over minus RA at X2. So FA0 1.5 mole per second, X2 0.8, X1 0.2. So bahagi dengan 4 ni kadang saya takut student confused. Minus RA kat bawah tu mesti pada X2 sebab yalah, dalam equation tu ada X2 tolak X1. Takut kamu confused nak tengok X1 ke tengok X2 punya minus RA. Kalau reaktor kedua dia mesti nilai minus RA pada X2. So when my X2 0.8 minus RA dia 0.013. So you calculate, you get the volume 69.23. Okay, so now you know, right? Minimum volume yang diperlukan adalah 69.23, but the reactor in my plant the volume is only 50. So the calculated volume is more than available volume, so we cannot use the second CSTR. So hence kalau satu tak boleh guna, we have to conclude that CSTR ni in series configuration cannot be used for this reaction. Okay, so perhaps you might wonder kenapa reaktor pertama volume kecil, reaktor kedua tiba besar. Kalau fikir logik pun, reaktor pertama tu conversion dia daripada 0 kepada 0.2 je. Tapi reaktor kedua ni besar kan, daripada 0.2 nak convert sampai 0.8. From 20%, I want to convert to 80%. So naturally, the bigger the conversion, the bigger the reactor will be. Sebab tu reaktor kedua volume dia besar sangat, tapi volume reaktor pertama tu kecil je. Sebab only 20% that I need to convert in the first reactor. Okay, so done. CSTR kita dah buat conclusion, tak boleh guna. Okay, so let us check PFR pula. Okay, so PFR, you see, okay, the first PFR1, okay, convert from 0 to 0.2. Okay, so saya dah tak explain kot part yang season 1 third rule tu kamu dah tahu kan, 3 point, so 0, final point 0.2, middle point mesti 0.1 sebab dia akan convert daripada 0 to 0.2 kan. So delta X dia 0, 0.1, beza dia pun mesti 0.1 ataupun tengok belakang 0.1, 0.2, the difference is still 0.1. Okay, so then you check from the table, make sure you check correctly from the table, okay, and then you calculate, you will get the volume 5.79 DMQ. It's okay, walaupun saya ajar cepat pun yang dalam saya punya soalan tu ada jawapan akhir. So, kamu faham? Kamu try buat kemudian, kamu compare dengan jawapan akhir. Kalau betul, most likely you do correctly lah. Okay, so done. So for first PFR, again, dia volume kecil je sebab conversion hanya daripada 0 to 0.2, right? So we get volume dia 5.79. Okay, so again, volume reactor yang kita ada kat plan kita 50. Yang kita perlukan hanya 5. So of course, the first PFR tu we can use. Okay, and then if you wonder kenapa PFR pertama tu even smaller than CSTR, ingat je balik Lewon's-Spear plot. Lewon's-Spear plot kan kalau volume CSTR kan area above and below the curve. Tapi kalau PFR, volume reactor dia hanya area below the curve. So PFR punya volume untuk conversion yang sama, volume PFR yang diperlukan of course will be smaller than CSTR. Tapi kita tak boleh cakap pula sebab kalau volume kecil reactor tu lebih baik. Tak semestinya sebab you have to see pula. If the reaction is liquid, most likely kita pergi CSTR. Kalau reaction to gas, most likely we go PFR. So there are other consideration as well. Okay, so then last one, PFR2. So PFR2, we are converting from 0.2 to 0.8 sebab reaktor kedua yang akan convert daripada X1 kepada X2. So the first initial point, 1 per minus RA at 0.2. Last point, 1 per minus RA at 0.8. Then don't forget middle point. So kalau 0.2, 0.8, middle point dia adalah 0.5. So part ni pun kena student lupa ataupun confuse nak cari titik tengah. 0.2, 0.8, titik tengah dia adalah 0.5. So let's say katakan kamu tak sure betul ke titik tengah dia. Kamu kira beza dia. Sebab katakan daripada 0.2 to 0.5, the difference is 0.3. Okay. Katakan kamu check belakang. 0.5 to 0.8, difference dia pun 0.3. So betul lah kalau difference depan, difference belakang sama, means your middle point is correct. Okay, so that's also one way for you to check. So means delta X 0.3. Middle point dia 4 per minus RA when my X 0.5. So same concept, tengok table. Make sure you calculate, you substitute the correct value. You will get the volume as 32.72 DMQ. So jangan lupa, compare balik dengan available reactor volume. Dalam plan saya, volume reactor yang saya ada 50. Saya kira yang saya perlukan hanya 32. So the calculator is smaller than available one. So we can conclude yang in the case of PFR, both reactors fulfills the requirement. So we can recommend to use PFR. So this is something scenario yang perhaps you might someday found in your own plan where you have to calculate, you have to use the available resources. Means you have to do calculation and determine whether the available resources boleh ke tak boleh untuk guna. Okay. So let's say pula case dia katakan mungkin you tertanya macam mana kalau dua-dua pun tak ada capai. Katakan let's say both pun tak boleh fulfill the requirement. Okay, there are few ways. Okay, one way is you can actually manipulate conversion. So maybe janganlah buat 20%, 80%. You can actually manipulate maybe the first reactor convert to maybe 40%. Second reactor 40 to 80 or first reactor maybe to 60% ke, second reactor 60 to 80. Perhaps. Then you might ask, macam mana kita nak manipulate conversion? That's where you have to then look at the reaction punya condition. Perhaps I have to manipulate temperature ke, pressure ke, or perhaps I can use catalyst ke, so on and so forth. So again, dia bila you reaction ni, that's the diversity. Bila kamu ada problem ni, actually banyak cara yang kamu boleh buat. Yeah, there's a lot of ways that you can actually manipulate. But again, dia tak ada one fixed rule. Sebab reaction, each reactions are diverse. You have to really understand the nature of the reaction to see what are the parameters you may manipulate to increase the conversion. Okay, right. So we are done. Okay, the last question. Okay, to be fair kan, sebab soalan 1 sampai soalan 6 ni saya dah terangkan secara mendalam. Okay, so question 7. I will leave it for you guys to do on your own. But as an incentive, somewhat similar question, takkan bulat-bulat jugalah. Somewhat similar question, I will come up either in test or in final exam. Okay, so I hope you have the time. Try attempt this by yourself. Jawapan akhir ada dalam soalan yang saya upload dalam VLE. Try it by yourself. If let's say you tak boleh buat atau tak dapat jawapan, you can refer to me. Just that I don't discuss this question in our tutorial. Okay, so I'm done for tutorial chapter 2 for today. So next week, I will continue for tutorial chapter 3. Please make sure you come for next week jugalah sebab kita nak cover untuk test. Test minggu satu lagi. So, if you understand the tutorial chapter 2, you understand tutorial chapter 3 next week, you should be okay for your test 1. Okay? So, if there are no questions, thank you very much for attending this tutorial. And I will see you next Monday for the next lecture. Thank you, everyone.
Right. Thank you, Doctor.
Thank you.
Doctor.